All right. Now we have Kevin, who's joining the lecturer's body. I don't know what's the title. And it's going to tell us about the detectors and the challenges in constructing detectors for the muon beams. So
Sure.
thank you very much for being our speaker. And there is a break at 11, where at 11 we get coffee break as every day for the rest of the week.
Okay, thank you. Yeah, so I was asked to give a few lectures on collider detector challenges, in particular the muon collider. So since there are four of them, I'll kind of structure them by, first of all, to the earliest lecture right now, it'll kind of talk about the overall goals and challenges of collider detectors and focusing on the particle interactions and detection basics. And then in the next lecture, which is not quite the next lecture, but there's one in between, I'll talk about tracking detectors, both inner detectors and muon spectrometer. And then later on in the week, I'll talk about calorimeters. And in the final lecture, I'll talk about R&D for future muon collider detectors, some things that are specific to that. So starting off, what do we want to measure with these detectors? Well, ideally, we'd like to measure all the particles that were produced in a particular interaction that we collide. And we'd like to measure their direction, their energy and momentum, charge, particle identity, lifetime, and which interaction it came from. And depending on the type of collider that we have, this problem can be, different parts of this problem can be easier or more difficult. And so this is just an example here of a proton-proton simulated interaction where you have more than one proton that is colliding. And so besides the event that you're actually interested in, there's all these other particles that are on top of that that you can see in the picture there. And so the question is, how do we identify those? How do we measure the particles of interest with all the precision that we want? And how do we separate the ones that we're really interested in the fundamental interaction from all of those other types of particles that may be there in the event? So what would an ideal detector do? Well, we'd like to do particle identification. We'd like to know what type of particles that we produced, whether it's a muon or a pion or an electron or any other particle. We like to make precision measurements of the energy and momentum of those particles. We'd like to determine its trajectory and origin, whether it came from the interaction vertex that we're interested in studying so that we can say something about that fundamental interaction, or if it came from some other source. So in the case of proton-proton collisions, that can be from the underlying event. It could be for another proton-proton interaction. Or in the case of, as we'll see, if you've heard about from muon colliders, it could be from a beam-induced background, or it could be a cosmic ray that just happens to interact with the detector at the same time. We'd like to have as full coverage as possible, right, of the full angular region, right, because of course we can't get actual 4π coverage because the beams have to come in, there have to be actual detecting elements, there's various cooling and channeling, but we like to get as full detection as possible over that period. But we also need to, on top of that, we have to take data at the rate needed for the experiment. We also have to choose, so some detectors and collisions can be run and collect every single event that occurs, but others need significant reduction of the rate or bandwidth and need something called a trigger in order to select the events that we're most interested in. We have to be able to cope with whatever radiation environment is present. We have to operate over a very long period of time. So in particular, some of these detectors will be run for decades. And we want to operate as the highest lifetime as possible. So if you imagine that you have a bunch of different elements of you have the machine, you have the detector, you have various parts of that detector, even at relatively high efficiency, if you have numbers that are like 90%, 90%, 90%, if you get 10, 20 of those things, the overall efficiency can get quite low if you have that. So you want to push it to as high as you can for each of those elements so that you can maintain the highest overall data taking efficiency. So the reality, of course, is that the things that are listed on those previous slides are not always and quite frequently not simultaneously achievable. So for example, you may want to put as many tracking elements as possible to get as many measurements as you can of a track that's coming through your detector. But on the other hand, that will add a lot of material, and you can degrade the resolution of different types of measurements. Also, there are real-world constraints, namely one we don't talk about a lot when we're actually when we're discussing detectors in general, but there's real-life constraints of money, right? So you can only build the detector that you can afford, not necessarily one that you might want ideally. And of course, real detectors have different have needs, like reading. You have electronic readout. There must have to be cables that are associated with that. You have to cool some of the electronics and some of the detectors. You have to have support infrastructure. The detector can't just float in space, right? You have to have something which is going to hold it up. You have to be able to have some scheme to be able to access it. Otherwise, it's like sending it into space, and you won't be able to make any changes to it if something goes wrong. And different collider types and that we've had, so the ones that we've done so far are E plus E minus, protons, and heavy ions, and maybe muons someday. And at different energies have different challenges, different background and radiation levels, which can lead to different solutions and different technologies. So if we take a look at some of those types of things that we want to examine, we'll start with a very clean kind of collision, which is an electron-positron collision. So these are some event displays from LEP, just to give you a sense of the different types of interactions that we see. So here, in the case of LEP, each collision is a fundamental interaction between two fundamental particles. We have an electron and a positron coming in. So almost all of these events, the idealization of looking at the Feynman diagram, and then actually what we see in the detector is something that we can make a one-to-one correspondence to. Events are relatively clean. So you can see here, this is from some LEP events for Z to dimuons, where you just have two pristine tracks going in opposite directions. Z to tau tau event, where you can see some hadronic activity here on one side and then a leptonic decay on the other. A three-jet event, and here is a little bit more complicated, W plus W minus event there. But relatively speaking, they're very low particle multiplicity in those detectors and those events. And the optimization really, therefore, is on resolution, trying to make it as precise as possible, complete reconstruction, and particle identification. If you contrast that to something like what we're seeing at the LHC currently, right? So this is actually an event that it doesn't have a particularly large pileup. So it had 11 reconstructed vertices, and now we're something like more like 40 or something like that on average. But you can see here, this is actually a Z boson decaying into two muons. And you can see it in this display, these two displays most clearly, that you have the straight muon tracks that go all the way out of the detector. And then, unfortunately, on top of that, right, in order to run at a rate in which we can get significantly of the events of interest that we're in, there's also 11 other proton-proton interactions which are superimposed on this. And so this is showing in the tracker as a function of the Z position along the beam. You have tracks that are coming from 11 different vertices. And so you have a lot of tracks in particles going through the detector that you can see both in the detector and then also in the calorimeter. And the reason it's run this way is that because while the inelastic cross-section for proton-proton interactions is quite large, the things that we're really interested in seeing, let's say, W and Z events, Higgs events, or possible supersymmetric events, have orders of magnitude, just orders and orders of magnitude smaller cross-section. And so in order to actually have a chance of seeing these, we have to run the experiment in which we get a lot of these types of events as well. And so we have to find a way to basically to select those interesting events out of those very high rate processes, which are more common. In the case of a muon collider, right, which of course this has never been done before, so these are just simulated events. The fundamental interaction between the two muons is similar, right, to the case of the electron-positron interaction. And so from a fundamental point of view of looking at, say we're looking at a mu-mu to a Z event, right, you would expect to see kind of a similar structure of relatively clean events in the final state. However, of course, that's at the hard scattering level. However, muons decay, as we know, right? So as they're going around, right, the accelerator, they can also decay, and then you can get electrons, which then can interact with the material upstream. And the next speaker will talk more in detail about this. And then the effect of which is to have showers. As you can see here, this is the case of one. Of one of the things that you can see is your production of the electrons and neutrinos, and then the electrons interact with the material, causing showers, which then cause radiation to come through those so-called beam-induced particles to come through the detector. And those can be another source of background which we need to actually take care of, just in the way that we, at the LHC, that we have those pile-up vertices and other events that we need to remove from the interaction. So what particles are we interested in detecting? So generally speaking, the detector only sees what we would call stable particles. Of course, stable here is a relative term. So that means basically having a lifetime that is long enough to interact with at least part of the detector, or that it'll travel on the order of something like 500 microns or more. And so the list of those particles, of all the particles that are in the particle data book, is much shorter, right? So there are things that are, as far as we know, are fundamentally stable, like the proton and the electron, which have an infinite lifetime, right, as far as we know. And then there are things which are like the muons and the pions and kaons, et cetera, which even though in our world, in the macroscopic world, have a very short lifetime, because of how fast they're going, they can actually travel quite far within our detectors, and certainly enough to interact with the detecting element. And so here in this table, the neutron's been even given an infinite lifetime in this case. Of course, a free neutron has something like a 10-minute lifetime or so, but that's kind of infinite on this time scale. So ultimately, if we want to measure those particles, it's going to have to interact with the detector in some way, right? And so ultimately, our detectors are resulting from interactions with the charged particles. The neutral particles have to transfer their energy to charged particles in order to be measured. And so those are generally seen mostly in the calorimeters. And then while neutrinos in principle, as you know from the neutrino program, can be detected, they're generally so weakly interacting that for our purposes, these basically go through our detector without interacting. Okay, so what do we want to do with the particle detector? Well, we had the properties here, the position and direction, momentum, energy, mass, velocity, lifetime. What kind of things are available in order to measure those properties? Well, we can, if we have tracking and position detectors, we can look at the curvature inside a magnetic field. We can have the particles interact with some material and try to measure its energy. We can try to do particle identification. We can measure the time of flight, et cetera. So the basic interaction of a charged particle goes back to this famous formula, right? That if you remember, it's called Rutherford scattering. It's the first thing probably you learned in your modern physics class, right? They tried to send something at a material and have it interact with the nucleus. And so there's this characteristic strong dependence on the angle, all right, in terms of the 1 over sine to the fourth. And it gives you the scattering angle. So essentially what you have is you have an incoming charged particle. It interacts with the target of a nuclear charge Z. And if you ignore spin and relativity, you get this classic formula from Rutherford scattering, which you've probably derived, right, in your modern physics class. And so because the nuclei are very heavy, there's very little energy loss for the incoming particle. It gets scattered. The nucleus doesn't move very much. The electron just gets bounced off it. And in fact, the average scattering angle is 0 if you take a look at the formula. And so, of course, in our detectors, these things don't happen, just don't scatter off a single nucleus. With a real detector with a finite thickness, the incoming particles interact many random times as they go through the material. And so the final displacement is a result of many of such of those scatterings. And from the central limit theorem, you expect a kind of a Gaussian distribution around the average value of 0. And then if you just have a single interaction, you do actually can see those Rutherford tails. And so the distribution is the electrons or the incoming charged particle goes through some scattering as it goes through the material, has some Gaussian distribution of the angle that it comes out in, and then has some non-Gaussian tails from the case where it really just interacts with one nucleus as it goes through the material. So you can calculate this, right? If you actually wanted to know what that was for what would happen if it's just interacting with the nucleus electric charge. However, because it leaves almost no energy deposition when it scatters with the nucleus, the thing that it actually leaves the measurement that we can see and use is generally scattering off of the electrons in the atoms themselves, right? Because those are lighter, and there has a larger probability of interacting with those as it goes through the detector. And so as the incident particle comes through, the electrons and the absorbed material that lead to the material lead to the energy loss. And as it scatters, it can ionize that material, which can be used as a matter of its existence. So you can calculate this. I won't go through the calculation. You've probably seen it before, in which you try to measure to see how much energy loss it would look for for a particular scattering. It's similar to the Rutherford cross section, but if you want to get it right, you have to remember that this is a spin 1/2 particle, and you have to take into account eventually relativity as well. And so if you take the differential cross section, and then you try to integrate it from some minimum energy to some maximum energy, you eventually can calculate that from the max basically is transferred if the incoming particle interacts and has a head-on collision and transfers as much energy as it can to the atomic electron. And the minimum one is a little bit more complicated since it involves quantum mechanics and a screening potential, but has a fairly simple answer. And if you go through all of this, you arrive at the famous formula, which you've already seen here before, which is the beta block formula. And so it has this characteristic function that at relatively low energies, the ionization is quite high. It drops rapidly as a function of the momentum, and then it has this relativistic rise as you get to larger momentum. But you note that a lot of the particles of interest, that for the types of processes that we're talking about, which has a momentum on the order of a GeV to hundreds of GeV. If you look at numerically, because this is a log plot here, this is close to the minimum ionizing potential for a lot, minimizing particle for a lot of those particles. And it's a little bit larger here, but it's still pretty close to a few MeV centimeters square per gram in these units. So that means that most of those charged particles that come in are going to leave a little bit of energy, right, on the order of this as they go through the material, if this was the only type of interaction that occurred with. So you can look at it in more detail if you want. You've also seen these plots from the PDG before. And we'll talk about what goes on up here. As you can see that this is true until you get to some critical energy in which then this turns over, and then radiative effects start to dominate, and you lose most of your energy through radiation at some point. Okay, so this leads to the first complication in this picture, which is called delta electrons. And so that as high energy particles are going through the material, they can transfer significant energy sometimes to some of those atomic electrons which they interact with. And they can cause the production or ionization of relatively high momentum electrons, which can then cause further ionization. And so those which are generally called delta electrons, where the electrons are ionized from the original high energy particle and themselves then have sufficient energy to continue this process as well. So if here's some examples of this, and when you have, here is the original particle that's coming through, and you see these little low momentum or low energy particles that are being ejected as the particle goes through. And those generally can complicate the particle, the interaction, and also can complicate your pattern recognition as you have these other particles that are being ejected as well. It can go through and form little tracks in your detector as well. And so this is an example here from a bubble chamber experiment where you have a high energy particle come in, and then you have lower energy electrons which are being ejected, and then because it's in a magnetic field are spiraling. So the second part of this is that when you get to high energies, as you already saw from the beta block formula, you can have radiation effects that start to dominate this as you get to high energy. So there's some critical energy here where the thing starts to grow quite large. And you saw that there was a qualitative difference when you got to the very high energy part of that, in which the particle was then radiating most of its energy away. So as you remember, classically accelerated particles, acceleration causes charged particles to accelerate, and this grows until it completely dominates the process. So this is the case for of electrons. So if we just ignore these other smaller processes that are also going on, but let's keep a simple picture. If we just have the ionization loss and then also the Bremsstrahlung, there's some critical energy, right, where it starts to become the dominant process. And at lower energies, it always exists, but it's a relatively small effect on the order of 10% or so. So if you really want to know the full correct treatment of this, you have to involve quantum mechanics, deal with spin, identical particles, and all of the processes. We won't go through that today. So in terms of that's the kind of the basic interactions that we're talking about for charged particles. And while the beta block formula gives you an average energy over a short distance, the actual thing that occurs, right, is that it's a series of different discrete interactions as the charged particle is going through. And that happens at kind of randomly distributed according to the rules of quantum mechanics. And this is particularly important when you're talking about fluctuations, because the actual sum of the energy loss is the sum over a discrete number of individual interactions that follow a Poisson probability distribution. And so generally speaking, you expect that those number of interactions are going to follow a Poisson distribution, and then as n gets large, it's going to look like a Gaussian, so we expect fluctuations of 1 over the square root of n. So if you actually start to collect data from this, well, you do see that the energy loss probability, right, looks like in some region that it's sort of Gaussian, right? But you notice that if you look at the actual measurement, it has these long non-Gaussian tails to it, right? And so this was observed quite a long time ago, right, when they started looking at particles passing through material. And it turns out that that will shift, right, the difference between the most likely value and the average one because of those long tails. So where do those tails come from? Well, those come from the delta rays. So there are additional, in addition to the energy coming through the primary incident particle, delta rays are also involved in the process. They can be produced and add extra energy. And so you get this larger tail to it. And this was calculated first by Landau in the 1940s. And he was able to calculate and come up with a theory that pretty well matches the data. So when you have some type of material here, besides just that average ionization that you're talking about, you can also produce these delta rays, which would then add to it. And so that kind of add this extra tail, basically, in that distribution. So in terms of continuing along this process, so far we've considered how basically a heavy charge particle would interact with the detector. But we also will produce electrons, right, in these machines. Electrons on the scale, if you look at where that critical energy is, it turns out is not very high, right? It turns out for electrons, the critical energy is on the order of MeV, in which the Bremsstrahlung processes start to dominate. So this really changes what we're kind of looking for when we're going to build a detector that's going to look for electrons, because we're looking for electrons on the several, GeV, hundreds of GeV scale, way above that critical energy, right? So while heavy charge particles will generally have that beta block energy loss. And so I'm thinking of like a muon, for example, which will go through our detector, not lose that much energy and leave a charged particle track. Electrons, in fact, will leave a large amount of their energy from a different process, which is that they immediately are above that energy for the ones that we're interested in. The electrons will immediately leave that energy through the Bremsstrahl process, which leads to a different set of interactions and therefore different detection methods. So if you look at that, that becomes the dominant process at high energy, or for electrons even at the MeV scale. You can calculate what that radiation is going to be. It turns out it has a very simple form, that it's proportional to the energy, and there's some constant. And that constant we call a radiation length. And so even poor me can solve this, this differential equation, right? Which is that, as we'll see, that we can integrate it rather easily. And so electrons basically will go through this process where you have electrons or photons, for example, that can continue to go through this radiation process. So you start with an electron. Because it's above the MeV scale, where Bremsstrahl is the most important process, it will radiate a photon. If that's above the threshold for pair production, you can then start to pair produce an electron-positron pair. And if those are above this critical energy, which is only MeV, so remember we're looking at hundreds of GeV electrons that are coming in, this process will occur over and over again very quickly. And we quickly go from a process where we had one particle, one high energy particle, to many, many lower energy shower particles. Eventually this process stops, right? When we get below that critical energy for radiating, or we can't have a pair production, and so the shower will stop eventually. So if you look, this is a bubble chamber version of this from quite some time ago, but they exposed a 50 GeV electron to a bubble chamber here, and you can actually track all the different electrons and positrons that were produced in the shower, and you can actually get a nice kind of like picture of what it looks like in the electromagnetic shower. So as I mentioned, even I can integrate this equation, and you find out that it has this characteristic exponential decay, right? So electromagnetic showers have this radiation length, which is therefore defined because of the exponential form of it, where they lose all but 1/e, or 37% of incident radiation energy. And so it gives us a qualitatively different picture, right, than the interaction with heavy charged particles, which just lose a little bit of energy and basically barrel through the material. For light particles where the radiation is dominating, they very quickly lose their energy in a very small, relatively small region of material in an electromagnetic shower. And so here just are some values for this, depending on if you put some heavy material like tungsten, lead, copper, et cetera, kind of the distance scale here in centimeters of 0.35 to 1 centimeter. So it's relatively a contained, shower that you will have in a relatively small area. If you want to form a simple model of this, there's this famous very old model in which you assume that these are the only processes that can occur are a radiation or a pair production. You ignore everything else. And you just assume also that, okay, we'll call the radiation length just basically is how long all of the particles will last, which of course it's not, it's distributed according to the exponential distribution. We'll also assume the energy is always shared equally. And so basically we just go through this process in a different number of generations where we split the energy from that one initial particle into a smaller and smaller, a larger number of particles with a small amount of energy. And it's a relatively simple picture, but it gives kind of the basic idea, right, of the shower that is occurring. And so the conclusion of that is that the shower depth is going to grow, right? The more energy that you have, right, the longer that process can occur. And it turns out that it's approximately like the logarithm of that energy. And so, which gives you the conclusion that even pretty high, because of the logarithmic dependence, even things that are pretty large energy, let's say if you go from 1 GeV all the way up to 1 TeV, the depth that the shower goes is only on the order of 20 to 40 sort of centimeters, right? So it's still relatively compact compared to other processes. And there's some material dependence that you can also, but it depends on how dense the material is, et cetera, how strong the electric charge is. And so finally, we'll talk about hadronic showers, which was given an overview basically of how the electromagnetic interactions interact with the detector. But we still have these other things, right, that we'd like to detect. We like to detect protons, neutrons, pions, kaons. They have the extra complication that they also interact with the strong interaction, right, that the electron and the photon did not. So if you look at a hadronic shower, the hadronic interactions, besides the fact that they have that beta Bach interaction, when they start going through a thick material, this can also cause a production of other particles, mainly pions, which are the lightest possible bound state. And notice that we already have a complication because there are three, right? There's the charged pions and there's the neutral pion. But if you remember from your particle physics class, the neutral pion decays almost immediately into 2 photons, and that will start an electromagnetic shower, right? So there's going to be a component of this, which is the hadronic interactions and interactions of those are going to be important, but intrinsically in every hadronic shower, there's also a component that's going to have electromagnetic shower from the decay of those pi zeros that are produced. In general, also the nuclear interactions are a little bit more complicated to 0th order in the EM case, the Bremsstrahlung and the energy loss, right, and the pair production are the most important processes. Here we can also have protons and neutrons, which are released from the nuclei. And critically, there's also energy which is intrinsically invisible or not measurable in our system. That is to say that when we break up the nuclei, there's that nuclear binding energy. We don't know how much energy a priori went into just breaking up the nuclei, the recoil of the target nucleus, and also the decay here of these pions includes neutrinos which escape the detector. So it's even in principle that there's energy that we can't really measure as a part of the shower process. So if you compare the two shower processes, we have in the EM shower, almost all the energy is going to eventually go into ionization. It's a continuous stream of events through ionization and radiation, which occurs rather rapidly in a rather contained area, where the hadronic particles, a certain fraction of the energy is fundamentally undetectable. So that's going to lead to fluctuations in what we can measure and what our resolution is going to be in measuring those showers. We also have loss through ionization interaction with the nuclei, and we also have inbuilt with them, a shower development that is similar to the EM shower, but on a different scale, because the probability of interacting with the nuclei for the strong interactions is less, just because there's more distance, right, between the nuclei as you go through the material. So if you wanted to know something about that EM fraction, you could also make kind of a simple model of that to say, well, on average, 1/3 of the pions that are produced are going to be the pi zero. And so every time that you produce a pi zero, we'll say that all that energy goes into the electromagnetic energy, and then it's a one-way street, right? Once that energy goes into that, we no longer see it anymore. And so after each generation of interactions, we lose a little bit more to the electromagnetic side. And you can come up with a kind of a simple formula based on this very simple model of how the electromagnetic fraction of that shower is, and it will look something like this. And it's not such a bad kind of model if you look at the energy, to look at the actual measurement of what fraction goes into the shower fraction. And of course, it's not a very detailed model, so it doesn't get everything completely right, but it kind of gives you the flavor for that. So the second thing, which is a little bit more complicated about the strong interactions, is that besides the energy which is released, right, in producing those strong interactions and producing pions and the nuclear interactions, we can also have different types of interactions in which we have a proton or a neutron which goes into a nucleus. Rather than immediately having an interaction, it excites it to some excited state, and then it sits around for a little bit and then decays. So while The prompt part of that, from the strong interactions, is basically instantaneous on our time scale. It happens. Pions are produced at least at the order of 10 to the negative 13 seconds, which on these experiments is instantaneous. There's also a component of where then the nucleus gets excited. It has some excited state, which then decays. And from human timescales, this is very short, but on the timescale of these processes, it can be microseconds. And so that's much longer than the timescale of the instantaneous interactions. So you can also have things in which energy that goes into some sort of nuclear excitation and then excites the nucleus, and by the time it decays, already from that event, and you're missing it in your reconstruction because you didn't see it until some later time. So it's not prompt in that sense. So this is like what we would call a spallation or an evaporation process of nucleons. So the other thing that we see is that because of the nuclear showers are governed by the nuclear interaction lengths, which is average distance for a high energy hadron to travel, these are the order of 10 to 20 centimeters for heavy materials. If you compare that to the radiation for lengths due to the electromagnetic showers, which are on the order of, if you recall, from 1 to 2 centimeters. So that means in general also that the hadronic shower is going to be deeper. It's going to go farther into the material. It's also going to be wider than that. And so typically what we're looking for an electromagnetic shower is a deposition in a material in a very small region of space, whereas the nuclear interactions can penetrate much deeper and be much broader into that material. So you can look at both the longitudinal, which is in the depth of the material, and the lateral, which is in the width. And so you have a core from that, which is the electromagnetic component from neutral pions, and then you have a tail from those hadronic showers. And so the leakage here actually decreases with energy because the fraction of the EM shower increases with energy. So that means you're getting more energy into that core as you go, electromagnetic core, as you go up in energy. So what does that have to do with how we're going to maintain our detectors? So that means that for charged particles, right, in the case that you have this classic picture here of this S-curve for muons going through CMS, is that for all of these charged particles, we expect if we put a little bit of tracking material, right, we'd be able to sense that they went through because they will interact a little bit with the charged particles. And you can see here is one example of that. And we'll start with the muon, in which just light interacts with that through all this material, just interacts basically as a minimum ionizing particle, goes all the way through the detector. And so we expect one track that goes through the whole detector. For cases in which you have things that can cause electromagnetic showers, well, like an electron, it has a charged particle, so we'll see a track in the inner portion of the detector. And then as soon as it interacts any significant material, it will have an electromagnetic shower and lose all of its energy very quickly. And so that's what we see here with this track leading to this small contained shower in the innermost portion of the detector. The photon here doesn't have any electric charge, so it doesn't go through that process in the tracker, but as soon as it goes through a significant amount of material in the first calorimeter, it sees it deposits all of its energy. And then here is a case of a neutral hadron and a charged hadron, which either leave a track or don't leave a track and then leave most of its energy. So these pictures are always a little bit confusing because as you see, the hadrons know nicely, they're not supposed to do anything until they get to the hadronic calorimeter, right? Of course, that's not true. They interact with everything as they go through. A better way to think of it is that we call it that because that's where it stops. So if you stop in the hadronic calorimeter, you're generally a hadron. If you stop in the electromagnetic calorimeter, you're generally an EM shower. And if you go through the whole detector and hit the muons, you're generally a muon. Of course, there are exceptions to that, but that's kind of a better way to think of it because, of course, we do expect the shower to start and also in the electromagnetic component of the detector. So when we move to discuss later, the background particles. So it's not only those particles from the the hard interaction that we're interested in, right? So this is the case of a single 10 GeV photon simulated. So you see this nice kind of like very small energy deposition in this very contained part of the detector. But unfortunately, because of all of those background particles that we get from the beam-induced background, we have also all of this soft energy deposition distributed everywhere in the detector. So we're gonna have to be able to think of a way in order to see this component of it on top of those background particles. And so just to give you kind of a little bit of a flavor for that for the next lectures, this Bib properties are, as it turns out, are predominantly fairly soft particles. So you can see here the distribution here in terms of the momentum and where they are in Z. So they also are strongly displaced because most of them come from not the interaction region, right? But they come from some showers downstream of interacting with the accelerator elements. And so if you look at the Z position, you know, as not something which is highly constrained around 0, but rather it's distributed throughout that region. And if you look at, in particular, the arrival time, well, there's some component, right, which is close to where the interaction occurred, but there's also a lot of particles that are very out of time, right, with the actual interaction that we want to see. So we can use those things, namely that they're soft, namely that they're displaced, and that they're out of time in order to try to reduce the impact on our reconstruction. So after the next lecture, I will continue this talk about how we build, therefore, trackers for the interdetector, muon spectrometer, and then go through the calorimeter case later, and then specifically talking about R&D for future muon collider detectors at the last lecture. Okay, thanks. I was watching, so.
Get a quick question.
Slides. I removed the part in the backend. Don't repeat too much.
So if you got a quick urgent question, of course, it's a good time now. Anybody?